Namaste. Welcome to Androidiots podcast. I am Anupam Singh.
I am Tushar Gupta. We talk about what's new in Android, best practices, and how to be a better Android developer.
Okay, guys. In the past 10 years, Android has fairly matured as an operating system. We started with very basic smartphone to very advanced wearables of today. And throughout this journey, users have interacted with the application which we developers make. But how Android manages these applications and how these applications interact with the operating system is something that we're going to explore today. And today we have Deepak with us. Deepak is a seasoned Android developer. He started his developer journey from Samsung, moved to Oppo, and he came to Glap recently. Okay, Deepak, can you walk us through the journey of Android?
Hi Anubhav, thanks for having me. So, before deep dive into these interactions between OS and apps, we should first understand the design considerations which were taken in the early stage of Android development.
Okay.
So, Android is fairly unique in the ways it allows multiple applications to run at the same time. Understanding its behavior is important for designing applications that will work well and integrate seamlessly with the rest of the Android platform.
Okay, can you please elaborate about these design considerations?
Sure. So there were the four key constraints considered when Android's multitasking was designed. So why these constraints were there? Because mobile devices have technical limitations and user experience requirements that are not present in the desktop or web systems. Firstly, Android came after the desktop systems. So there is a great difference in application usage pattern in them. So in desktops, user have to close the application with a cross button. But in Android, if you see our usage pattern today, we open and close applications frequently throughout the day. And Android designers did not want to require that users close applications when momentarily done with them. Second, mobile devices don't have the luxury of swap space, so have fairly hard limits on memory use.
Deepak, can you briefly explain what is this swap space for our listeners?
A swap space is nothing but an extension of RAM. The least recently used files in the RAM can be swapped out to your hard disk until they are needed later, so that new files can be swapped in to the RAM. It is inherently slow, so we'll get back to it because there are some nuances around it.
Okay, fair enough.
Third, application switching on a mobile device is extremely critical. Target was to keep this switching time as low as possible. This is especially important because a user can switch between a few applications like opening a new SMS message while watching a video and then returning to the same video. Any noticeable wait in such situations will quickly make users hate the system. Fourth, there is a all applications are equal philosophy. All available APIs must be sufficient for writing the built-in Google applications as well as third-party apps. So there should not be a special treatment for Google apps. So if we look at the first two requirements, they highlight an interesting conflict. Designers did not want users to worry about closing their apps, but rather make it appear that all of the applications are always running. So at the same time, mobile devices have hard limits on memory use. In Android, why we do not have something like swap space is because designers did not want an did not want to have applications open in the Android system and but still they are not performing well. For example, in desktop computer we have swap space, but it quickly degrades the performance of our desktop systems. Why? Because it needs 2 page RAM to its swap space. So hence because swap space is something which is there on our hard disk, and loading applications from swap space to RAM, then to show to the user is something which will take more time. So we did not want to have something like that on Android.
Oh, that's why the desktop application keeps desktop as a whole keep getting slower.
Yes, so, yeah. So that's the main reason.
Okay.
So these competing constraints were a key motivation in designing Android process.
Okay, as you said, Android apps are not closed by the user. So when does an application actually stops?
Okay. Uh, First, let's talk about a very common misunderstanding about Android multitasking. So there is a huge difference between a process and an application. So these are not tightly coupled entities in Android. So applications may seem present to user without an actually process currently running the app. Multiple applications may share the processes, or one application may make use of multiple processes depending on its needs.
So Deepak, so when I see an application's process running, does it mean that it's doing anything?
Actually, we don't know. It may simply be there because Android needed the process at some point and has decided that it would be best to keep it around in case it needs it again. So, this is the key. Android does not shut down processes cleanly. When user leaves an application, its process is kept around in the background, allowing it to continue working, for example, downloading web pages if needed, and come immediately to foreground if user returns to it. If a device never runs out of memory, then Android will keep all of these processes around. So truly leaving all the applications running all of the time.
Okay, so what I understand is that devices have limited memory, and to accommodate this, Android decides which process to keep and which to kill.
Absolutely. So this is what has led to Android's process lifecycle. The rules of the process lifecycle are based on how important a process is for the user's current experience and how long it has been since the process was last needed by the user.
Hmm.
So once Android determines that it needs to remove a process, it does this brutally, simply force killing it.
Wait. What do you mean by brutally killing it?
Well, to understand it, we need to know kernel position on it. The kernel can immediately reclaim all the resources needed by the process without relying on the application being well written and responsive to a polite request to exit. It allows the kernel to immediately reclaim application resources, makes it a lot easier to avoid serious out of memory situations.
Okay, and what happens when a user returns back to this brutally killed application?
Okay, if a user later returns to an application that's been killed, Android needs a way to relaunch it in the same state as it was last seen. To preserve the experience, as we mentioned earlier, all the applications are running all of the time. So this is done by keeping track of the parts of the application that the user is aware of. For example, activities.
And the fragments and all the views.
Yes. And restarting them with the information about the last state they were seen in. So important to know for a developer is that the last state is generated each time when user leaves that part of application, not when it is killed, so that the kernel can later freely kill it without depending on the application to respond correctly at that point. So in some ways, Android's process management can be seen as form of swap space. Application processes represent a certain amount of in-use memory. When memory is low, some processes can be killed, which means swapped out.
Mhm.
When those processes are needed again, they can be restarted from their last saved state, which is swapped in.
Okay, Deepak. So, what is an application in the Android OS?
Okay, so first let's understand what is the how Android OS treats an application.
Mm-hmm.
So the Android operating system is a multi-user Linux system. So in which each application is a different user. So the Android platform takes advantage of Linux user-based protection to identify and isolate application resources. So this isolates apps from each other and protects apps and the system from malicious apps.
Okay.
To do this, Android assigns a user ID, unique user ID, which is UID, to each Android application and runs it in its own process. Android uses this UID to set up a kernel level application sandbox. The kernel enforces security between apps and the system at the process level through standard Linux facilities such as user and group IDs that are assigned to apps.
Okay. So a small sandbox is created with a unique UID.
Yes.
But how does an application interact with the Android OS then?
Yeah. So it's very interesting to know. So each process has its own virtual machine. So an application's code runs in isolation from other apps. The Android system implements the principle of least privilege. So let's just focus on this principle. So it means each app by default has access only to the components that it requires to do its work and no more.
Okay.
So this creates a very secure environment in which each app cannot access parts of the system for which it is not given permission. So by default, apps can't interact with each other and have limited access to the operating system. By default, every app runs its own Linux process. The Android system, or we can say Zygote, starts the process when any of the app's component need to be executed, and then shuts down the process when it's no longer needed, or when the system must recover memory from other apps.
Okay. Okay, Deepak. So when I think of Zygote is predominantly a black box for various Android devs out there. Can you please elaborate a little bit about it?
Yeah. So let's understand first what is the meaning of Zygote word. So it is the initial cell formed when a new organism is produced.
Okay.
So in Android, Zygote is a special process which handles the forking of each new application process. So these processes are simply regular Linux processes. We may think of the Zygote as a template process for each application or service that is started on the device. So it is launched by Android runtime, which also starts the first virtual machine. This virtual machine then calls Zygote's main method,
Okay.
which causes Zygote to preload all the shared Java classes and resources into the memory. So we may think of it as a warmed up process, ready to be deployed at a later point of time. Each new Zygote process is a child of original Zygote process, and it includes a VM. So with each new request to launch an application, a new process is forked and a new VM is created, and then that application is bound to the thread of this process. So each application runs in its own Linux process with its own thread. We may think of each process as a software component container.
Okay. Can you just please elaborate about these containers that you're talking about?
Yeah. So these software component containers are once loaded. So they hold activities, services, and content provider components of the application.
Okay.
And due to preloading of these shared libraries, it makes them readily available. So when a new application is requested, it launches within a milliseconds. Each new application then receives a map and not a copy of the classes.
Okay.
So this dramatically reduces load time of applications. So it is an optimization made to accommodate the limited resources available. So because each container receives a map, these resources are shared between applications. And each new fork of VM does not need to keep its own copy of classes and resources. So it is a Linux. It is this Linux kernel feature which is called copy on write, which enables this functionality.
Okay.
So remember, at this point, Chaigar process still hasn't started.
Okay.
Still, it has to receive a call from activity manager to launch an application. But the container is prepared, and once the call comes in, that specific application package will be loaded into the VM, and finally, then Zygote starts the system server before settling into a listening mode on its socket for request to eventually to be sent to activity manager.
Okay, Deepak. Okay, so what I can understand is when I see our launcher applications and I see all those apps, social media, all those apps are there. So the moment they are there, yes, user has not clicked on them, but these containers are ready with all the shared resources.
Yes.
And Zygote is there in a listening mode and it has opened its socket. Whenever user will click, I'll start the further application process.
Right.
So what happens when user actually clicks on the application then?
So this is a very interesting question. So do you know about main UI thread?
We have heard about it
From where the name main comes from?
Absolutely no.
All right, I will explain the whole story. So when any application is launched, a lot happens behind the scenes on kernel level. That is bootstrapping the Zygote, loading classes into the JVM, and for the JVM to locate the Java main method, and then finally invoke it. So in case of Android, JVM locates the famous public static void main method in the activity thread class,
Okay.
which many of us do not know,
Mm-hmm.
since there is no main method in our activity class. So this is the point where kernel hands over control to your application. So now we know that main method exists in the activity thread class. So whatever is triggered from this main method is called main UI thread.
Okay.
We have found the entry point, the activity thread,
Mm-hmm.
but there are still multiple steps between the main method invocation and your activities on create method.
Okay, can you just deep dive there a little bit more, Deepak?
Yeah. So let's first understand this main method. So once it is invoked, so it does few important things. Basically, three important things. So it prepares the main looper, then it set up a handler, then finally calls the looper.loop method on the main thread. So preparing the main looper. So in this step, the main looper is set by calling looper.prepare main looper method. So this marks the current random thread as application's main thread. So this right here is how the famous Android main thread or UI thread is designated.
Okay.
Then it calls the handler. So within the activity thread class, so there is a private inner class called H. So just the name is just H.
Okay.
So this extends the handler class. So it instantiates the H handler so as to serve the thread's main handler.
Mm-hmm.
So what's cool about this H class is that it contains over 50 event definitions.
Mm-hmm.
So that your application can be, for example, launch activity, pause activity, bind service.
Okay.
So all those activity state changes and everything about activity.
Resides here.
Only this H handler handles all those things.
Okay.
So then finally it calls the loopers loop method. So after the main thread has been designated, in order to work to take place on main thread, so the main thread calls loopers loop method on the main thread. So this begins the execution of messages on loopers message queue. So now the main thread is up and running and can begin processing tasks of the queue. Note that if looper.loop ever terminates, the app will exit the loop and then throw a runtime exception. So this suggests that the loop method should ideally never prematurely terminate.
Okay, Deepak, why do we call looper as looper?
Yeah, so it is very simple to understand. So we call it looper because it loops over a list of messages that are given to it. So the list is infinite. It's referred to as message queue. If you look inside the looper source code, so it has a for loop with no terminating condition. It never terminates until the message sent is null. So now we have a main method running thanks to the looper. And we already know that handler adds messages to the message queue and handles it whenever looper dequeues them.
And how these entities come together when the activity gets launched?
Okay, so to finally answer your question, what happens when a user clicks on the app icon? So one important thing to remember is that all this looping and handling has been happening within the main method of our activity thread class because that's where they were invoked.
And how do these entities come together when the activity gets launched?
Okay, an important thing to remember is that this looping and handling happens in the main method of our activity thread class because that's where they were invoked. So the handler in activity thread class we talked about before. So it is responsible for handling every message that's received in its own handle message method. So this is where the interesting part is. So this handler handles over 50 messages like resuming an activity, pausing it, starting it, binding services, handling receivers, flagging low memory or trim memory warnings. All these are handled here. So even launch activity is one of these cases. So a method called perform launch activity is invoked here, which returns an activity object. So by this time, this activity object already has some crucial information like instrumentation, context, component, and intent information, which is required for the activity. So now the final step is when instrumentation class method, which is call activity on create. So this method is invoked here, and which calls perform create method of the activity class, and this perform create method it calls on create method of our activity. So at this point, like your activity has been loaded with tons of useful variables and methods that can be used to basically create your awesome new application, Android app. So this is all thanks to activity thread and some smart thinking behind handler and the looper framework.
Deepak, this was amazing to learn actually. If you talk about the journey, let's say how when I write a simple code and I write an activity and this market has launched an activity to learn that what actually happened just before and what the method calls are called just before that on create of my activity is called what method calls are called, or how looper is involved in doing that before that, or how before clicking an app the system creates these containers and Zygote is there listening to these events on various ports, and even before that how Zygote spawns a different process and carves out a memory space for itself. It was just a fascinating to learn what about this entire application launch, let's say life cycle, if we have to name it somehow. I guess just thanks for it from my side, and also from the I guess the whoever listeners are going to listen, even they are gonna say just one word, I guess, that they are flabbergasted. Okay, thanks Deepak. Thank you again. Thank you very much. It was a very nice session from you. I really hope that you come to Androidiots podcast once again and enlighten us with all the basic Android fundamentals and take us forward. Cheers.
Cheers.